Hello fellow scholars. Today I'd like to present a question that I came across while solving a few CodeChef problems. Now its code is conflip. You can check it out in your browser. So before I solve this question, I'd like to give a fair warning. You don't really need to do this mathematical side to get this problem. You can just get some Python code to brute force it and count a solution for you. But today I'd like to get into the mathematical side of why the pattern in the problems exist or not. So let's get into it. So the problem goes like, given n coins all placed in a row with all of them being in an initial state of tails or heads. So that means all the coins are all tails or all heads. That's the initial state in which they're placed. And so we're playing n rounds, which is equal to the number of coins placed. In the ith round, obviously restriction on I as 1 to n, we flip the side of the nth coin and all the coins before it. In the ith round, flip the side of all the coins with position less than or equal to I. Now, after 10 rounds, what is the number of tails or the number of heads? Now, I have two approaches for this problem. Approach one is, I think it's a little bit of overkill, but you can look up that. The first approach is good old induction. Second one is coin by coin counting. This is a fairly simpler one. So let's take a problem before I actually get into using the approaches. Now say you have 3 coins, and without loss of generality I'll be assuming that all of the initial states are tails. It doesn't really matter, you can replicate the same proof for the heads one, so it doesn't really matter. Suppose we have 3 coins, all of them is as tails. Alright, I'll be bigger. Now the game goes like this. So we play 3 rounds as there are 3 coins. In the first round, that is I equal to 1, we flip this. Now since there are no coins before it, we don't have to do anything else. We go to the second round, we flip this becomes head. We go back, flip this to tails, come back, flip this to heads, again flip this, flip this. You see that the resultant sequence that we get is heads, tails, heads. Now we are supposed to find the number of coins which are heads or which are tails. Clearly there are 2 heads and 1 tail. Now let's take an even number of coins case. Suppose we have 4 tails, right? We do the same thing. Actually, I'll let you do this. It's a pretty simple iteration to do. We have tails, heads, will be the resultant. Now we can see there are 2 tails and 2 heads. Don't you see a pattern here? If it's even, then there are 2 tails. If it's even, it has half the number of tails, and naturally the remaining coins, half the number of coins are heads. In the tails case, the number of heads, that is the opposing side coins, is the number of coins plus 1 by 2. Now I'll just present this over here. So the number of coins, let's say k coins, right? K coins. Then k by 2 are tails, k by 2 are heads. If k is even, now if k is odd, then k plus 1 by 2 are heads, then remaining naturally being k minus k by 2 minus 1 by 2, that's equal to k minus 1 by 2. K minus 1 by 2 k minus 1 by 2 tails if k is odd, right? Now let's pick off where we left. Now, as per my induction hypothesis that half of them are heads and half of them are tails, if it's even. Let us prove that by induction, shall we? Now, suppose we have two t coins. Well, 2t, where t is an integer. Suppose we have two t coins where t is greater than or equal to 1. If t is equal to 0, obviously there will be 0 coins, and that does not make sense. T is equals to 1, greater than or equal to 1. What I propose is that after the game, 2t by 2 or t are heads and t are tails. Now I prove this by induction. Let's proceed by induction on t. On the base case, when t equal to 1, the lower limit of this inequality, we see that there are two coins, because 2 into 1, right? Tails. The resultant is tails, heads after you finish the game. So clearly the induction case checks out. Now let's get into the induction step. Suppose it holds for t equal to t minus 1. It's a bit non-rigorous but fairly understandable. T equal to t minus 1, it holds. Then we need to prove it for t equal to t. It's standard induction procedure. Prove it holds for t equal to t. Okay, let's build off of this case. In this case, we have 2t minus 2 coins. In this case, we have 2t coins. So what we shall do is, we'll append these extra 2 coins here to this chain after playing 2t minus 2 games. That is, after the number of coins games, that is 2t minus 2 rounds are played. We'll be left with a chain like down. As we suppose it holds for t minus 1, then there should be t minus 1 heads and t minus 1 tails as per the induction hypothesis. Now we have appended 2 extra here. Now to finish 2t rounds, we need to play 2 more rounds. This gives us heads, tails, so on and so forth. This is t minus 1 heads, t minus 1 tails, and we have changed this to head, this remains a tail. After this, it again comes back to the original chain, heads, t minus 1 heads, t minus 1 tails, heads, tails. So here's one extra head added to this, so we get t heads. Now here's an extra t, we add it to this, we get t tails. So we have proved it for the case when t is even. Now let's prove it for in the case when t is odd. Sorry, not t is odd, when the number of coins are odd. Now suppose there are 2t plus 1 coins. Then what we can do here is, by breaking this 2t plus 1 coins into 2t coins chain and the single coin chain. Now this allows us to use the induction hypothesis that we have proved for the case when the number of coins are even, that is 2t. So let's add this 1 coin after playing the 2t rounds. We'll be left with tail heads, heads. Now this 1 coin extra, we'll play 1 more round to get 2t plus 1. Heads, tails, then tails, heads. Yeah, so here we know that as per the induction hypothesis, there are t heads, there are t tails. Now add this extra heads over here. this gives us t plus 1 heads. T plus 1 we can rewrite it as 2t plus 1 plus 1 by 2. Therefore, we have proven it for the general case when t is even or t is odd. Now, let us utilize our approach 2, which is coin by coin analysis. Now, in the case 1, let's suppose that we have an even number of coins. So, there are 2k coins over here, and in this case, notice that every tails which is placed in an odd position goes through an even number of flips. This one goes through 2k, this one goes through 2k minus 2, and this one goes through only one. This is an odd position, right? Doesn't matter. So this one goes through 2k. So when the number of flips are divisible by 2, it will trivially return back to its original state at the end of the game. Therefore, by exploiting the fact that for every even integer, there exists the half the number of odd numbers less than or equal to them, k odd, k even, and we can utilize this to prove that we have exactly half of them, which is k heads, exactly half of them which are k tails. Now let us go ahead and check the case when the number of coins is odd, right? Suppose we have tails, t 2k minus 2k plus 1. Now notice here that every coin placed in an odd position goes through an odd number of flips. This one goes through 2k plus 1, this one goes through 2k minus 1, and so on and so forth. So this reverts to head, this remains the same, this reverts to head, and clearly we can see that there are let's count the number of odd numbers less than or equal to one odd number, shall we? It can be 1, 3, 5 until 2k plus 1. Using the general formula of arithmetic progression, we get that 1 plus the number of terms, that is L represented by n minus 1, and the common difference is 2, equal to 2k plus 1. Let us cancel this one. Am I doing this right? Yeah. Cancel this. So we see that there are k plus 1 odd position numbers less than or equal to an odd number. Now, as I've said, this odd position valued letters revert to heads, and naturally there are k tails left which remain the same. Therefore, I have proved it using the second approach. Second approach is slightly less rigorous, and I prefer the good old induction if I were to solve this in a math contest or a math Olympiad. Thank you.